Assalamualaikum, students and fellow physics enthusiasts. Welcome to Circuit's physics tutorial. In this episode, I am going to discuss an example of a nuclear transformation, a radioactive element that spontaneously emits an alpha particle. How do we determine the energy released and the kinetic energy of the alpha particle? You will know the answers by sticking around, watch, and learn. The question is, household smoke detectors contain a tiny amount of radioactive americium that decays by alpha emission to neptunium. The given nuclear reaction equation is as shown. The atomic masses are 241.056827 atomic mass unit for americium, 237.048172 atomic mass unit for neptunium, and 4.002603 atomic mass unit for the alpha particle. If the americium nucleus is originally at rest, find letter A, the total energy released in the decay. Question letter B, find the kinetic energy of the emitted alpha particle. And question letter C, find the speed of the emitted alpha particle. The nuclear transformation described in this problem is when radioactive americium emits an alpha particle and transforms into neptunium. All right. The nuclear transmutation is given in this equation. All right. Americium has a mass number 241 and an atomic number 95. When it emits an alpha particle, which can also be represented as a neutral helium atom with 4 as its mass number and 2 as its atomic number, americium decays into a neutral neptunium isotope with 237 and 93 as its mass number and atomic number respectively. Given the atomic masses of the nuclides involved, we are to determine the following quantities. Letter A, the total amount of energy released in the alpha decay process. Letter B, the kinetic energy of the emitted alpha particle. Take note, the americium nucleus is originally at rest. So for question letter C, we are to determine the associated speed of the alpha particle. Moving on now to our computations. To find the total energy released in the alpha decay, all right, we first calculate for the mass defect or the mass deficit delta M, which is simply equal to the atomic mass of americium minus the combined atomic masses of neptunium and the helium nuclide. So substituting the values and doing our math, okay, we get the mass defect delta M equal to 0.006052 atomic mass unit in four significant figures. To calculate for the equivalent total energy released, we simply multiply the mass defect delta M by the conversion factor 931.5 million electron volts per atomic mass unit. Okay? This conversion factor is based on Einstein's famous equation E equals mc squared, which conceptually simply means that the mass difference delta M between the original nucleus and the combined atomic masses of its products has an energy equivalent which obeys both the laws of mass conservation and energy conservation. Alright? So substituting the computed delta M, alright, equal to 0.006052 atomic mass unit times, alright, the conversion factor 931.5 million electron volts per atomic mass unit, okay, we get the amount of total energy released, which is equal to 5.637 million electron volts. All right? Also in four significant figures. For question letter B, finding the kinetic energy of the emitted alpha particle, we take note that the total energy released, which is equal to 5.637 million electron volts, becomes the total kinetic energy of the neptunium nucleus and the alpha particle. Since the radioactive americium was originally at rest, all right, its initial momentum is equal to zero, right? Now, when it emits an alpha particle and decays into a neptunium nucleus, all right, the momentum of the neptunium nucleus, labeled here as p sub 1 prime, and that of the alpha particle, labeled p sub 2 prime, must in fact be equal, okay, in magnitude. This is following the law of conservation of momentum. All right? So, in this equation, for the kinetic energy, which is equal to 1 half mv squared, or when expressed in terms of the momentum, the kinetic energy can also be equated as p squared, or the square of the momentum, divided by twice the mass. All right? So we can see that the kinetic energy is just inversely proportional to the mass. Right? So what does this mean? It suggests that the kinetic energy shared by the alpha particle, all right, since it is less massive compared to the neptunium nucleus, is in fact 98.33% of the total kinetic energy, or that is 237 over 241, all right, times 5.637, which is the total kinetic energy, all right, 5.637 MeV. So if we do our math, then the kinetic energy of the alpha particle will just be equal to 5.543 million electron volts. All right. Also rounded to four significant figures. Lastly, to find the speed of the emitted alpha particle, we can convert its kinetic energy from the unit million electron volts to joules, all right, which is 8.880 times 10 to the negative 13 joules. All right, that is the equivalent of 5.543 million electron volts in joules. All right, we obtain this by simply expressing, all right, or by multiplying uh, the kinetic energy in million electron volts by the conversion factor. All right, 1.602 times 10 to the negative 19 joules is equivalent to 1 electron volts. So when we multiply this conversion factor by the given kinetic energy already converted to electron volts, that is 5.543 raised to the 6th power electron volts, okay, we will get this kinetic energy in joules. All right? So, to calculate for the speed v, using the formula square root of twice the kinetic energy divided by the mass m, okay, we first express the atomic mass of helium nucleus, all right, 4.003 atomic mass unit, in terms of the unit kilogram. All right? So, the atomic mass of helium, which is 4.003 atomic mass unit, is multiplied to the conversion factor 1.661 raised to the negative 27th power kilogram per atomic mass unit. All right? So, doing our math, we will get, all right, after substituting completely the given data in this working equation for finding the speed of the alpha particle, all right, the given kinetic energy already expressed in joules that's 8.880 times 10 to the negative 13 joules, all right? Multiply that by 2 and then dividing it by the uh, atomic mass of the alpha particle or the helium nucleus, already expressed in kilogram, 6.647 times 10 to the negative 27 kilogram. Right? So, when simplified, we will get the value of the speed of the alpha particle emitted, which is equal to 1.634 times 10 to the 7th power meters per second, also in 4 significant figures. So we are done. All right? Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.